Good day, ladies and gentlemen. This is Sarel van Grenen, aka Mr. VG, and woo, today is going to be a fantastic and amazing day because we are going to be looking at Euclidean geometry, specifically the question 10 of the Department of Basic Education, November 2021 paper. Now, this is a beautiful sum. I loved this sum. It incorporates so many things from grade 8 right through to grade 11 mathematics. When we look at Euclidean geometry, this sum specifically, I'm going to encourage you to try this sum yourself, okay? Give it a shot. Give it all you've got. Make sure you can do it. And if you are getting stuck somewhere, try again before you look at the rest of this video. So hit the pause button and try it yourself. When I look at this, ladies and gents, you will see one of my things that I always will tell you to do is to mine for information. So let's go through the information, good and proper. So in the diagram, BE and CD are diameters of a circle having M as a center. Automatically, ladies and gents, I think of the definition. Now, the definition of a circle means, or it implies, that there are radii. So I love to first of all put in my radii, and after I've put in my radii, I always look for isosceles triangles. In this case, there are no isosceles triangles, so that's fine. Next up, I'm going to look at theorem 1, 2, and 3, which has to do with centers of circles. If I look at theorem 1, it says that if I have a line from the center of the circle, so from M to AE, if that line is perpendicular, then it bisects the angle. Or the side, sorry, it bisects the side. My apologies there. So if it is perpendicular, and it is, we see that with AE being perpendicular to CD, then AF is equal to FE. There is another line from the center, but it goes to this chord there. But we don't even know what that point there is. So I'm not going to look at it. Okay, you might not even have spotted it, but I spotted it as I was recording this video. Okay, let's look at theorem 2. Theorem 2 says the angle at the center is twice the angle at circumference. Please be careful, ladies and gents, of this one, where M1 relates to A2, because I'm using this there. Okay, so it goes from M to C and from M to E and M to C, and then it comes together again at A. So M1 is 2 times A. The same, ladies and gents, is going to happen if I go from M to B and to D, and then they come together at A. So M3 is twice A3. Okay, that is very important, and later on we are going to use especially A1 and M1. But there isn't more to be used there. So I'm going to carry on to question 3, or theorem 3. Theorem 3 has to do with diameters. Now, this is important, again, because they very specifically tell you there are diameters. So first of all, if I look at the diameter BE, and that comes together, that one didn't come out nice, from B to E, and that comes together there by A. So therefore, A2 and 3 must be 90 degrees. Also, there is another diameter, diameter CD, which comes together there by A. And this means that A1 and 2 are also 90 degrees. Fantastic, 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 fantastic. The next bit of information, it says the chord AE is drawn to CD. AE is drawn to CD and it cuts at F, and AE is perpendicular to CD. Let angle C be equal to X. I don't have more information, but I mustn't forget to think about, first of all, tangents, okay? There are no tangents, so I'm not going to worry about theorems 7, 8, or 9. Then, cyclic quads, don't forget to look for them. There are cyclic quads, but none of the theorems 4, 5, or 6 are applicable, so I'm not going to use it. Again, ladies and gents, don't just run into your questions. Look actively for tangents. Look actively for cyclic quads. Now let's look at the actual questions. So I've taken that sketch. I've cleaned it up a little bit, and this is what I've got left. First question, give a reason why AF is equal to FE. Well, I've got a line from the center, and it's perpendicular to the chord. Remember to look at the acceptable reasons. You don't just write your own reasons, especially if you are in a public school. They are very strict on the reasons, so please make sure you know your reasons. Next up, they say, determine, giving reasons, the size of M1 in terms of X. So what I love to do is now, okay, what do I know about M1? M1 is my monkey. But I've got a number of mountains that's standing in my way. First of all, M1 relates to A1. Okay. If I look at A1, because remember M1 is twice A1, A1 actually relates to angle C and angle AFC because they are in that triangle together. Because that triangle adds up to 180 degrees. The angles, the interior angles add up to 180 degrees. Let me get my terminology on 100% spot on. So, I'm going to say A1 plus angle C plus angle AFC must equal to 180 degrees because of interior angles of the triangle. Let me explain my logic to you. If I can find A1 in terms of X, it means I can find M1 in terms of X. That's my logic that I'm using here. So let's substitute in those two values we've got. C is X and angle AFC is 90 degrees, which means angle A1 is 90 degrees minus X. Well, how did I get that? Well, again, I subtracted 90, and I subtracted X on both sides. So 180 minus 90 is 90, and then I subtract that X as well. Okay. But now, M1 is twice A. Why is that? Because the angle at the center is twice the angle at circumference. Therefore, M1 is twice 90 minus X. In other words, M1 is 180 degrees minus 2X. Ladies and gents, please, look out for these kind of ones that look like this. We have got a circle, I've got the center, and it comes together at the circumference. That wasn't a nice one. There we go. They love to ask this, where that inside angle is twice that angle. And students miss it every single year. In all my years of teaching, I've seen kids miss this so many times. Now, ladies and gents, I've answered the question. The question was, determine the size of M1 in terms of x. Okay. Writing it in on the sketch is very important for going forward. So let's have a look at the rest or the next question. Prove, giving reasons, that AD is a tangent to the circle passing through A, C, and F. Oh my goodness, ladies and gents. Please, please, don't tell me, oh, but AD is a chord, therefore it cannot be a tangent to a circle. That's not what we are asking. We are asking, is AD a tangent to that imaginary circle there? Ladies and gents, oh, my matrics every year go, oh sir, but AD lies inside a circle. It cannot be a tangent. I know that in the big sketch, but what we are asking you for is, if I had to draw an imaginary circle around A, F, and C, would AD be a tangent to that circle that's not drawn? That's the question. Okay, that is the big question. But how do I do that? That is the important thing. So how do I do that? By proving that A2 is equal to C. Why is that? Remember Theorem 9's converse says that if that angle there that I am double highlighting is equal to that angle inside, then it is a tangent to that imaginary circle. So what do I know about A2 if I think back to the right at the beginning? Well, it relates to A1. Okay? A2 relates to A1. Why? Because together they add up to 90 degrees. Remember angles in a semicircle. So that is my thought process. That A2 and A1, the sum of them is 90 degrees. Angles in a semicircle. If I substitute what I've got for A1 into that equation, and I solve for A2, I get x. So understand, ladies and gents, there I now have x. So what did I actually want to prove? That A2 is equal to C and they're both x. But we've done it. So now we just write it down for them. A2 is equal to C, which is equal to x, and therefore answer the question. AD is a tangent to the circle passing through A, F, and C, or AC and F. Ooh, this is a beautiful question. Okay? I love these questions, and the examiners also love this question. Now, I'm going to clean up my sketch a little bit for this next question, question 10.4. Oh my goodness, how beautiful is this question, this 5-mark question. Now, I am going to take you down a rabbit hole like Alice in Wonderland, okay? And maybe halfway through, you're going to look at me and go, sir, what on earth? How on earth did you think about doing this? But I'm going to tell you my logic in any case. And then the funny thing is, when I looked at the memo, I realized actually I could have solved this sum in about 5 lines instead of 2 whole slides. But I'm still going to take you down my logic because you don't know what you're going to get in the prelims or in the finals. So let's talk about the monkey behind the mountains. In other words, the real problem that I want to solve and the obstacle standing in its way. When we talk about this, let's fill in the information that we've got. AB is 24 and CF is 6 units. Could have been centimeters, could have been millimeters, but they decided upon units. If I think about AE, it lies right next to a 90 degrees. So I'm thinking about Pythagoras. But for me to think about Pythagoras in triangle ABE, I need a 90 degrees. But very technically, I've got that A2 and A3 is 90 degrees because of angles in a semicircle. But I do have to state this for the examiner if I want to use it. Don't just go, oh, but it's indicated in the sketch. No, you've got to write it for the examiner. Okay? You have to write it proper for the examiner. So what I'm going to do is I'm going to look at Pythagoras in triangle ABE. So AE squared plus AB squared is equal to BE squared in this triangle there. Okay, everyone all right with that? Okay, I hope you're all right with that. Then I'm going to ask myself, why was the 6 given? So I'm going to make life a little bit easier for myself by letting the radius be x, or not x, r, because it stands for radius. Now you will see on this sketch that I indicated Fm as being r minus 6. Why? Because Fm is the radius minus that 6 units. So if I want to go towards Pythagoras in triangle FME, look what I'm doing now. Now I'm going to that small triangle there. Okay, I'm going to that triangle there. If I go towards Pythagoras in that triangle, okay, I am going to think about that AE is actually twice FE. Remember, we had that right at the beginning. That was the first question that was actually asked of us. Why is AF equal to FE? So in triangle FME, I can use Pythagoras with ME squared and FM squared plus FE squared. Substituting the values I've got for R, I'm going to try and see, can I not solve for R? But I'm sitting with a problem. I have the length of ME as also being R because it's the radius. But I don't have any length for FE. Oh my goodness. What now? What now? What I'm going to look at is, let's just see how far we can go with this. So I'm going to simplify this and see maybe I can get an expression for FE. So I'm trying to isolate FE squared and seeing where does it lead me. The beautiful thing is my R squareds actually cancel out. They become 0 because I am having R squared minus R squared. This means I've got an expression for FE squared. Why is that, ladies and gents? Well, let me take you down the rabbit hole. Oh, I'm going so deep in mathematics. Basically, I'm trying to solve, let me explain, these two at the same time. I'm trying to solve simultaneously. So just bear with me, please. I'm trying to solve this simultaneously. If I look at what was given, I'm trying to relate AE squared, remember that's the original Pythagoras one that we have, to this new bit of information. Well, AE is twice FE. So I'm substituting the values in. Okay, let me not go too fast there. Remember that AE is twice FB. AB I have as being 24, and BE is 2R because it is twice the radius. It's a diameter. Remember that, ladies and gents? I'm going down a very amazing rabbit hole here. I'm going to now simplify this as far as I can. So I'm distributing out my brackets. Now, don't I have an expression for FE squared from the previous slide? Well, yes, and I am going to divide by 4. But remember that FE squared is 12R minus 36. Remember that from the previous slide. So that means I'm going to substitute that in. FE squared is equal to 12R minus 36. Boom, I've got an equation with one variable in it. I can solve for R. So I've got a simultaneous equation which I'm going to factorize, and I've got R as being either 18 or negative 6. Man, this is fantastic. But I'm starting to doubt at this moment whether I went the right way, because remember, this is only worth 5 marks. But I've got R. That is fantastic, because if I've got R, I can find BE, which is 36. So I can use Pythagoras because I've got AE. Remember what I'm doing now is I'm going back there. I'm going back there. I've got R, so I've got BE. Now I can find the length of AE as being the square root of that. And that leads me to AE being 12 root 5. Oh my for 5 marks. All of these calculations from there to there, 5 marks. Oh my goodness. I don't think I went right with my thinking. The sum is right. I got the value. But ladies and gents, it was only worth 5 marks. So what did I do? I cheated, okay? I cheated. I went to the memo and I looked now. After I got this value, I went to the memo and I looked. But isn't there an easier way? And there was, ladies and gents. If I look at the information that was given to me, first of all, AF is equal to FE. So F is the middle of AE. We also know that M is the middle of BE. So M is the midpoint. Grade 10 triangles, ladies and gents. Therefore, FM must be a half of AB because of the midpoint theorem. I laughed so much with this sum. And this means that the radius is 18 centimeters, which means I could use Pythagoras in that triangle there and get the length of EF. Oh my goodness. Using Pythagoras, I can just solve FE. And therefore, I have a value for FE. Timesing it by 2, I get the length of AE. Ladies and gents, it's been amazing. Thank you very much for tuning in and staying with me. Have a beautiful rest of your day. Cheers.